So now we're going to compute the second part of this question. And we're going to start off by using the integral formulation of Gauss's law. We're already given what E is, and we have to find dA so that we can integrate and find the charge enclosed. So again, I would recommend bookmarking del in spherical coordinates, because on that same web page you also get this diagram over here. And what this tells us is the volume element for each component. So again, in Gauss's law, we're integrating over a sphere, the surface of a sphere. So we want this region over here. And this region is just this term times this term. So we have r d theta times r sine theta, which is r squared sine theta. There's a d phi in there. R squared sine theta d theta d phi. And that's exactly what our dA is. So again, multiplying that out together now, we have E, which we've already computed from the first question, to be kr cubed r hat. And our dA, notice our dA points in the r hat direction, so it's an r hat. So doing this integral now, we get kr cubed r hat dot dA dot r squared sine theta d theta d phi, also r hat. So notice that we're dotting r hat with r hat, and that's exactly equal to 1. And since the integral has no r dependence, we can take r cubed and r squared outside, same with k, and we can then evaluate this integral. So k r to the 5 integral of sine theta d theta d phi. Now, how do we choose the bounds for this integral? Well, notice here that we're integrating over the surface of a sphere, and that d phi goes in this direction. It's going around the circle. So it's going to go from 0 all the way around, which is 2 pi. So our phi integral is going to be from 0 to 2 pi. And our theta integral, well, to get the area of the circle, now that we've gone from 0 all the way to 2 pi, we need to go from the top to the bottom. So we need to go from 0 down to pi. So that's going to be our bound for the sine theta integral. And then we're just going to compute what this integral is. So kr to the 5, 0 to 2 pi, cos theta from pi to 0. Again, the integration constants will cancel out each time, so we can ignore that. Now, cos theta graph looks like this. So at 0, it's equal to 1, and at pi, it's equal to -1. So we just evaluate that. One minus -1, the first value, and then we subtract the second value. And that's equal to 2, which we can pull outside of this integral. I don't want to forget to write the d phi's. And then we're integrating from 0 to 2 pi for d phi, which is equal to 2kr to the 5 times phi, evaluated from 0 to 2 pi, which is exactly equal to 4 pi k r to the 5. Now, we know that all of this is equal to q enclosed over epsilon naught. So that allows us to find out what q enclosed is. Four pi k r to the 5 epsilon naught, which is exactly the answer we're looking for. So great, we've done it one way, so now we have to do it another way. And the other way to do this is to just look just above in your book for Griffiths, and it actually gives you a volume integral for the total charge enclosed. So the total charge enclosed is equal to the volume integral of the charge density. And in the first question, we already computed the charge density. That was 5 epsilon naught kr to the 5. Now, how do we compute this volume integral? How does that work? Well, we know that we're going to integrate over the volume of a sphere. So all we have to do is take the volume of a sphere and work backwards from it. So v is equal to 4 over 3 pi r cubed. And then we take the differential, which is basically just taking the derivative with respect to r. dv over dr is equal to 4 pi r squared. Therefore, dv is equal to 4 pi r squared dr. Notice we could actually do the same thing for the question above. Instead of doing a double integral, if you guys haven't learned how to do double integration yet, you can just take the area to be 4 pi r squared and then compute backwards from that way because you don't have any r dependence. So that's another way you can hack your way through this integration if you haven't done volume integration yet. So great. We integrate dv to be 4 pi r squared dr, and we have the value for rho. So therefore, we integrate 5 epsilon naught kr to the 5 times 4 pi r squared dr. That doesn't seem right. Yeah, it's not right. Oh, no, that's right. dv is exactly equal to 4 pi r squared dr. And where I'm going wrong is I wrote the charge density wrong. This is actually a 2. So my apologies, I apologize. And now we have all the terms that we need. So great, we have 5 times epsilon naught times 4 pi times k integration of r to the 4 dr. And we're going from 0 to some arbitrary radius r. So doing this integral, we get 4 pi epsilon naught k times 1 over 5 r to the 5. Evaluated from 0 to r. That gives us exactly the answer we got before. 5's cancel out. There we go. One thing to note is that if you are doing it this way for the first question, if you haven't learned integration yet, then you'll have to find dA, which is equal to 4 dA over dr, which is equal to 4 pi r times 2, I believe that's a derivative. And then you get dA over dr and you substitute that into this equation. So what that does is you get, let me just zoom in for you. You get the integral of E dA, which is kr cubed times 4 pi r dr. And then you integrate this from 0 to r. That should give you the same answer, and you don't have to worry about double integrals. So that's just another way to do it if you haven't learned multivariable integration yet. But that should be it. Again, I emphasize the Dellin spherical coordinates is a fantastic resource. And for all the physics majors out there, I highly recommend that you bookmark this. Even in my upper years, I found that I was constantly referring to this website. Thank you very much, everyone.